Hello students, the next topic is linear mappings. Before starting, let's take care of some terms. Our textbook author is using the term mapping, and this is a term I use more often, map, and sometimes people use these. Transformation or transform, not as a verb but as a noun, and finally function. They all mean the same thing. In analysis, most of the time we use this term, function, but in geometry or in algebra, depending upon circumstance, we use various terms. Conceptually, they're all the same, the definition and everything exactly the same, but for some historical reason, sometimes we use the term mapping, sometimes transformation, and so on and so forth. Okay, here we go. Let's begin. The definition of linear mapping. Let V and W be vector spaces and a map or function. L, which is defined in vector space V, targeting the vector space W, is called linear if it satisfies these conditions. Number 1, preserves addition. Whether I add before or after doesn't matter. Number 2, preserves scalar multiplication. Number 3, preserves zero vector. Here, this zero vector, as a matter of fact, is a zero vector in vector space V, and this one over here is zero vector in vector space W. But if there's no danger of confusion, I'm not going to bother putting these capital V and capital W. One more comment. The last condition here is not really that important. Just like the subspace condition where we had zero vector belong to that subspace. I hope everybody remembers that. This can be dropped exactly by the same trick. Here, you can put in c equal to 0, and let's see what happens. If I plug in c equal to 0 here, if this 0, and if that's 0, what do we get? We get L of 0 times V. It's a zero vector, isn't it? It's just that this is a vector in vector space capital V. And this is equal to 0 times some vector. That's also a zero vector, except that this is a zero vector in vector space W. And that's exactly the same as this one. So it's not really necessary, but it's useful as a matter of fact. And how useful is it? Kind of like subspace. If you have to disprove something, some candidate of a subspace is actually subspace, or prove that it is not a subspace, in that case, this one was really useful. The corresponding property for subspace was really useful. Likewise, if you have to prove some function is linear or not, looking at this is going to be quite useful. For example, let me cook up a problem. If sum f of x equals to 3x plus 1, linear map in R1. Well, you can check this or that, but it's much easier to check this one. Plug in x equal to 0 here, and do we get 0? The answer is no. But these kind of problems are not as trivial as the subspace examples. How about this? Capital G of x is 3x squared plus sine of x. Is that a linear map in R1? Well, if you just use this one and plug in 0, then G of 0 is 3 times 0 squared plus sine of 0. Yes, this is 0. So if you plug it into this, it looks like it's working. But of course, if you plug it into these, either this or that, then you can show that this is not a linear map. It's rather clear. I mean, we have quadratic term here and we have transcendental term here. It's not going to be linear. You have to have first degree, by the way. Okay, those were rather trivial examples and non-examples for linear maps. Trivial, I said, because I took examples from one-dimensional case. Let's go a little bit higher dimensional, like these examples. Here's a nice example, arguably the most important example in this set. Let A be a m by n matrix, and let X be a n-dimensional column vector, and Y is m-dimensional column vectors. Then the map given by this, y equals to ax, is a linear map. What if I asked you to prove it? Can you prove it? By checking these three. Well, the last one here, the third condition, is not really necessary, so let's not worry about this one. And just concentrate upon these two. Let's see. Can you prove it? L of x1 plus x2, is this equal to L of x1 plus L of x2? Is this true? Well, let's check. L of x1 plus x2 is nothing more than matrix A times x1 plus x2, isn't it? By definition. And then we can use the properties of matrix multiplication. It's distributive. So A x1 plus A x2. And what is this? Is this L of x1? And is this L of x2? Yes, indeed. So yeah, we just proved this one. And can you prove this one on your own? I'll leave you there. So yes, matrix multiplication is a good example for a linear map in arbitrary dimension, n dimension to m dimension. So if you have an m by n matrix, that is sending n dimension to m dimension. This is arguably the most important example of linear map, and we're going to come back and discuss in far more detail in second section of this notebook. Please remember this example. It's very, very, very important. Far more important than all the other examples put together. Nonetheless, let's go to the next example. Even if it is far less important than this one, it's a nice example anyway. Let's see, we have a infinite dimensional vector space, a vector space of all continuous real functions defined in a closed and bounded interval a and b, and we define I of f as an integral. So can you prove this is a linear map like this? Can you prove this? And then the second one is, of course, I of f, c times f is equal to c times I of f. Can you prove this? Well, let's discuss it very briefly. I of f plus g, by definition, is integral, isn't it? But integral of which function? F plus g. Now, can you use the property of the integral? Is this true? Certainly true. We have been using this since Calculus 1. And this is I of f, and that's I of g, isn't it? So yes, we can prove it, and we can prove it easily, as a matter of fact. How about this one? I'll leave that to you. Similar proof and similar argument applies to differentiation, the derivatives. And okay, here's rather weird example. Okay, let's talk about this briefly. This is rather weird and it exceeds the kind of level I want for this course, but the purpose of linear algebra is not just linear algebra itself, but preparation for other courses as well. So let's talk about it a little bit because we're going to be talking about things like this in some a little bit higher level courses. So we can consider real number not as a number or point, but we can consider real number as a mapping. So given x a real number, we can define capital F of x given by the real number, which is sending a function to another real number. Here's an example. So let's take x equal to 2. Let's take x equal to 2. And then f of t is t squared minus 3t. f2 of f, hey, just plug in x equals to 2 here. T equals to 2 here. So t squared 3t, so plug in t equals to 2 there and do the computation, we get negative 2. So this capital F of 2 is sending this function, small f, to negative 2. Another example here, u of t is t squared. Okay, that's a real function as well, and then plug in t equals to 2, the same deal. That's what this capital F of 2 does. Plug it in, do your computation, that's 4. How about v? v is t, plug in t equals to 2 and I get 2. And now here's a punchline. f2 of u minus 3v. Let's calculate that, u minus 3v. Well, you can separate u and then minus 3v. You can separate like this. And then you can take this negative 3 out. So we get like this. And let's calculate this one. And we know that's 4. And then this one, we know that's 2. So what do you get? We get 4 minus 6, which is negative 2. Hey, same as before. That's just an example, but you can actually set up arbitrary addition and scalar multiplication and prove that this map is actually a linear map. A little bit weird example because the real number x is working as a function, and then small f, which is a function, and that is acting like a point. And x is sending f to y. It's kind of strange to think of these kind of things, but there is a duality, and this happens to be an important example. I don't know whether I'm going to have a chance to deal with this in differential equations 1, but definitely in diff equal 2, this will show up. These are rather theoretical examples, and let me see. Before moving on, let's take care of one more thing. I shouldn't have closed this. It is possible to combine these two, preserving addition and preserving scalar multiplication, into a single expression, preserving linear combination. Can we actually prove it? Well, the proof is left to the students, I said, and whether to leave it as a homework problem or non-required exercise set, I didn't make my decision yet. It is quite likely that I'm going to make this into a homework problem. In that case, you really have to sweat it out. Don't worry, we already went through the key details of exactly the same type of problem before when we dealt with subspaces. So don't be intimidated, but nonetheless, this is going to be a challenge. You see, this is if and only if problem. So you have to prove both directions. So assume these two are true, and you have to prove this. Okay? And then the other direction. Assume this is true for all vectors v1, v2, and scalars a1 and a2. And then you have to prove this and prove that. So you have basically three things to prove. Assuming these two and proving this one. Another, assuming this, you have to prove this, and then you have to prove that. There are three things to prove here. I'll leave you there, and we're going to move on to the next topic in the next video. Thanks.